We can look at another way to view natural transformation between two functor f and g going from a to b. In the previous video, we've introduced this category b over f, whose objects are triples, ba and some arrow in b, going from b to f of a. And the arrows in such category are pairs of arrow S, which belongs to B, and F, which belongs to A, which joins the first component and the third component of those triples, such that when we apply the identity functor to S and the F functor to little f, the square that we can draw commutes. So we've defined objects, arrows, and we obviously have to define composition and identity, and composition of such arrow in B over F. So composition of a pair of arrow will be defined as the pair of composite arrow, and the identity in this category B over F, where morphisms are pair, will be a pair of identity. And you can check that it's the neutral element for composition. We've defined that for B over F, but we can do the same for B over G, and it's exactly the same principle. Now, if you remember, the natural transformation was a collection of morphisms, alpha A prime, one for each object of A, such that for any morphism F in A, the corresponding square can commute. Now, given those three things, B over F, the category B over F, the category B over G, and those square alpha defined by the natural transformation, a natural idea would be to say, can we post-compose stuff in B over F with alpha to get elements in B over G? That is, can we somehow define a functor from those two categories, B over F to B over G? And indeed, if we want to formalize that idea, we will try to define this alpha star for post-composition, which would take a triple and map it to the other triple whose middle component is obtained by post-composition by alpha A, and who will map arrow SF, so arrow from B over F to arrow from in B over G. And I mean, we hope it's an arrow in B over G, and so that means we have to have the rectangle in the middle commute. And it does commute because the first square commutes by definition of the morphism in B over F, and the second one commutes because alpha is a natural transformation. So both square commutes, which means it doesn't matter which path we choose going from B to GA prime, they all denote the same morphism. That is, GF alpha AU is equal to alpha A prime f of fu equal to alpha A prime Vs. So the pair SF, which is untouched as a pair of morphism from the pair SF in B over F, the pair SF is a morphism in B over G. So not only have we defined a functor alpha prime, which respect composition, identity, etc., but it furthermore has the property that if we forget the middle component and just consider the domain and the codomain, the first and third component from our category B over F, this triangle in cat commutes. That is, we start from some triple in B over F, and we look at the index B and A. We will land on the same index if we first apply our alpha star or alpha bar, and then we forget the middle component. We start from the same B, we arrive at the same B, and we start from the same couple BA, and we arrive at the same couple BA. So this triangle commutes. Now this construction can be functorialized in a way. To each f, we've defined this forgetful functor, LF, from the category B over F to B cross A. And for alpha, we've defined this L alpha morphism such that it commutes. So it means we have a functor from the category B exponent A, a functor from A to B, to cat over B cross A. And it's functorial because the composition of natural transformation is defined by postcomposition, and our L alpha, L beta is also defined by postcomposition. So we have this equation which are necessary for L to be a functor. And this construction L has furthermore an interesting property, is that it is full and faithful. Now what does it mean? It means for a fixed pair of objects f and g in B exponent A, for any two such objects, we have an isomorphism between the Hom set, that is all the set of morphism in B exponent A from f to g, that is for each natural transformation, we have one and one only morphism in the arrival category between LF and LG. So we've seen how we go from alpha to L alpha by postcomposing. Since it's postcomposing, means if we have equality L alpha equal L beta, we have obviously alpha equal beta when we consider the identity. So that entails it's a definition of being faithful. And to see that it's full, we need to pick up some gamma in cat over B cross A, and show that it's the image of some functor, some natural transformation gamma bar through this transformation. So it corresponds to one and one only gamma bar. Now, how could we define gamma bar given some gamma? Well, we will start with the identity on f of a. So this triple is an object of B over F, and it defines an object in B over G, and we will define this middle component from f of a to g of a as gamma bar. Now, is it a natural transformation? Well, means since for any morphism in B over F, we have a morphism in B over G, the pair f of F is certainly a morphism in B over F, because the middle square commutes, which joins f of a to f of a to f of a prime, or f of a to f a prime to f a prime. And so the resulting square, f of a to g of a through gamma bar a, then g of f will be equal to gamma a prime bar f of f. So we have indeed a natural transformation gamma bar. And to see that if we reapply the transformation back, we have the same gamma. We can consider the applying L gamma bar, and if we pick up some object in B over F, we look at what the image is. So we have to postcompose by not alpha a bar, but gamma bar by gamma a. Sorry. By definition of not alpha a but gamma a, since the first the left part is in u1 f of a, u1 f of a is a morphism in B over F, we will have a commutation of this square by the property that gamma and not alpha is a functor. So it means we have the same, we have the equality of those two morphisms, L gamma bar U and gamma U. So that means our functor, functor L is full, that is, for each morphism in the cat over B cross A from LF LG, we pick up one such morphism, and it's the image of a morphism gamma bar from BA-FG. So the fact that it's full and faithful is interesting in some in other context. If we pick up A to be the category 1, which consists of only one object and one morphisms, then functors from A to B are akin to objects of B. And the previous theorem says that the morphism between B and C within category B is equivalent to cat over B, LB, LC. Now, through a construction through the fiber functor, if you know a little bit, I mean, we can construct from LB, a functor which, given some x, looks up all the objects in B over B whose domain is x. And obviously, if we pick up a morphism from Y to X, then any morphism from X to B will be mapped to a morphism from Y to B. So we can indeed construct a functor, B underscore little b, which is just a fiber functor of LB. And so this theorem says that the previous slide was saying that the morphism between B and C is equivalent to the pre-sheaf functor YB, the morphism between the pre-sheaf functor YB to the pre-sheaf functor YC. And said otherwise, this functor Y is full and faithful, which is some form of Yoneda lemma, which can also be derived by the full Yoneda lemma. Now, in a previous video, we've seen those natural transformation as a functor from the category A to this category F over G that we constructed, which is the general form of those category B over F and B over G. It works for any functor. And this category is actually a pullback in cat. So to define an arrow from A to F over G in cat is to give ourselves a pair of arrows such that the different color, the composition of those two functors commutes. That is, delta 0, delta 1 composed with this red arrow will be equal to the functor F cross G composed with the former green arrow. And if we have a pair of such functor, then it defines uniquely a functor from A to F over G. And we can check that if we give ourselves this gamma from B over F to B over G, we can indeed define such a pair of functor. So it uniquely defines a functor from A to F over G, which is a natural transformation by previous slides. Now, to sum up, the point of this video was this correspondence from the category B exponent A to cat BA, and we've gone from this seemingly complex notion of natural transformation, and we've reduced it into a functor between category who have B over F and B over G, which have some kind of power pact built in a way. And so those categories happen to be the category of elements of the pre-sheaves, etc., etc. But it's really all about post-composing and seeing some functor as a set of trajectories. And with alpha, we can continue trajectory which lands on F. We can pursue them, we can continue them, and transform them into trajectory which lands on G.